welcome to the Hinted Neuron podcast. I'm still your host, Kelvin Pascal, and I know it's been a while. It's actually been a year since I have done an episode. I've been doing more writing and working on more projects that involve writing or editorial work, which is why I've not been able to dedicate time to the podcast. But I think my larger goal for the year is to do at least 6 quality episodes. And so that could be once every 2 months or however I see fit. In any case, I had a conversation with Ayomide. I've known Ayomide for a while, and he's really been an amazing person, an amazing friend through the years. We've talked a lot about ideas in the machine learning AI space. There was a time when we would have these technical conversations about what was going on in the field and all that stuff. And he is a member of technical staff at Qroq. He's been into AI research for a long time now. I think one of the things I like about him is that he's always reaching for depth. He wants to find like the depth in things, like the things he wants to do, he goes deep into them. And so this is why I like him, and we had a very good conversation around AI, the state of AI right now, the ideas in the space, some of the history of ideas in the space, and what to expect, what's next, and how to best prepare for that future. I really enjoyed the conversation. I learned a lot, and I think that you might learn a lot too. Stick around for the next, 1 hour, 30 minutes. If you enjoy this podcast, don't forget to like and subscribe on Spotify, Apple Podcasts, YouTube, wherever you get your podcasts. Leave a review or a like or a comment, and make sure you keep sharing this podcast. I know I'm not as consistent as I would like to be or as people would like me to be. And I know people have been asking me when next I was going to drop an episode. So there's an episode for you right now. So keep sharing. And now, here's my conversation with Ayomide. I'm here with Ayomide. Ayomide, thanks for coming on the podcast. I've been looking forward to this conversation for a while now. How's it going?
Yeah, good. Thanks for having me.
Yeah.
I'm a bit nervous, but yeah, thanks for having me.
No, it's fine. Yeah. Yeah, I think we've been talking about this podcast for a while now, but I wanted to give you sort of like how I usually do this. I give you the opportunity to talk about yourself for like 1 minute, and then we can delve into the conversation.
I mean, talking about myself it's a really hard thing. I find it a bit pretentious to talk about myself.
Yeah.
So I'm Ayomide, member of technical staff at Qroq. I currently work on reasoning and agents, mostly the agent side of things. I got into AI in late 2017, I think late or mid 2017, thereabout. And initially I studied mechanical engineering, but yeah, it wasn't really interesting enough for me to pay attention. So I ended up spending my time reading mathematics and physics, then eventually landed in machine learning and AI, and spent some time after school to self-learn most of the existing papers back then. Yeah, been lucky enough to work in a place like Qroq.
Yeah, this is actually really interesting because when you said you studied mechanical engineering, I just remember that we actually went to the same school, but like I don't think we interfaced. We only interfaced after both of us had graduated. I think.
Yeah, exactly.
Yeah. So like how I actually met Ayomide was that sometime I think in 2020 or 2021. I think most likely in 2020. I made a tweet about a book I was reading. I think some sort of consciousness book. And so you actually commented on that tweet and we got talking from there. I think it was like a book on consciousness, panpsychism, and like the different arguments for and against consciousness. And I think at the time, I was sort of like trying to get into some of the neuroscience of like neuroscience side of things, coming from reading about just purely AI, pure AI methods and stuff at the time. I think a lot of people weren't calling it AI at the time. We were mostly like a machine learning community on Twitter
Mm,
at the time.
mm,
Yeah, but it's really interesting how the field has evolved. I think we've like even back then a few years ago, we've always had these conversations about like some of the progress in the field, especially ethics. At the time
mm,
when
mm.
people were
Yeah.
talking about AI ethics at the time, we've had that conversation even when like people who were doing AI ethics at Google, AI ethics at
Mm,
Google as at maybe 2019 ish, we were having that conversation, and and it's surprising now that it has become more of a big thing than it
yeah.
was, and we were talking about like some like laws, social science side of things, but really is interesting. I don't know what's like for you right now. I wonder what you're thinking about ethics. I don't know. We've not had that conversation in a while.
Yeah, to be honest, I think it's been a while I've had a serious conversation on AI ethics. I think in the industry and whenever I converse with people, usually people approach it from a safety research perspective, or I might be wrong, but what you have now is kind of like AI safety, right? So
Hmm. Yeah.
you want to make sure that the model follows the user instruction, but at the same time, um, you want it to be as safe as possible, right?
Hmm.
And I think people kind of figured out that post GPT-3, you could prompt the model, or you could have the model behave in a certain way through prompting. So now people set up this kind of like system prompt to just give bunch of instruction to the model, and in there you include all the safety rules you want the model to actually follow, and you expect the model to follow it, right? So
Yeah.
yeah, that's one of the things people talk about. It's been a while I've really seen ethics work that cut across the social sciences in recent times, or to how I think everybody is kind of concerned about how AI would impact our world.
Yeah.
But because at the same time people see it as a really, really big opportunity that is going to make impact, I think all those things are sort of take a backseat, or I might be wrong, but it's been a while that I've seen really concrete things around that, right? Probably
Yeah.
because and I work mostly in the industry, and
Yeah.
it's something that's not pop up on my radar in a long time actually.
Yeah. And I
Mm.
think because if I look at some of the trajectory of like certain AI companies like maybe the super intelligence company, I think the SSI, I think that's what they're
Mm,
called,
yeah.
and maybe companies like Anthropic, for example, or some of the companies that spun out of OpenAI, people who left OpenAI to start their own companies, or even people like Temnit Gabriel, who
Mm,
worked at Google AI Research at the time. A lot of them have research labs right now, and they're doing work, but like they some of them left either the big labs like Google or OpenAI just to start their own thing because of this concern for safety and ethics at the time. It's just like diverging opinions from OpenAI.
mm,
But not to linger on that, I want to talk about the way we're doing like inference today. And
mm,
everybody, like, I guess what's mostly called AI today is big giant LLM models,
mhm,
550 models at like around 700 gigabytes in weight.
mm,
And they're deployed on like compute infrastructures and stuff to billions of people at a time, and
Mm.
which hence why we're seeing a lot of data centers, a lot of like RAM prices, going up, GPU prices going up, because a lot of people are actually, a lot of manufacturers for hardware themselves are leaving the consumer industry because there's more business in like data centers and all. Yeah. So
Mm.
yeah, I want to get your thoughts on what you think about LLM, just like the history of it, for example, because we started from this place of going from, maybe I would say, attention is all you need, and then
Yeah,
going
yeah.
to Google Birds, from Google Birds, and where we have right now mostly decoder only models, if I'm remembering correct, like decoder only models, like the ones that are
Mm.
being used
Mm.
today. So, and then pre-training and then reinforcement learning. So yeah, take us through that journey.
Yeah, I mean, um, the attention is all you need paper kind of like kicked off most of what we have, right? Although there is a paper on attention which was applying attention to LSTMs, I think it was in 2015. And then you have another paper on reading comprehension with attention, which I think introduced self attention. Sorry, I forgot most of the two papers, but there was the machine translation paper in 2015 by Bengio and one other researcher, and there was another paper
Mm-hmm.
from I think University of Edinburgh on self-attention. And then you have the attention is all you need paper in 2017. I think the
Yeah.
major thing about the attention is all you need paper in 2017 was the fact that they completely removed the idea of LSTMs and recurrent neural networks and replaced the entire architecture with just these self-attention blocks, right?
Yeah.
And at first, the reason for that is to maximize parallel computation, right? You don't want a case where you do this recurrence where you have time steps, and at to get to time step one, you have to do computation at time step zero, get your output, then you do time step one, and you keep going in this recurrent manner, right? So you can process the tokens in parallel, right? And it's so funny that um, the original attention is all you need paper, because we now know from the Flash attention work by the guys from Princeton, that is Tridal, that the original self-attention was actually slow because it wasn't IO aware, so they made it a lot faster. But then it became clear that you could do this massive parallel computation with just attention alone. And then OpenAI kind of picked up on that really fast. And then I've forgotten if I think Ilya in one of his talks mentioned that they were already playing around. He, alongside Alec Radford, were already playing around with massive data sets on emails and trying to see training the model on this massive email data set and seeing what the output looks like, but in the LSTM setting. So immediately they saw the attention is all you need paper, it became clear that this was what they needed to
Mm-hmm.
scale, right?
Mm-hmm.
So the GPT-1 came in, and GPT basically means generative pre-training, right? You
Yeah.
introduce this concept of pre-training where you have this self-supervising signal, which is the next token to be predicted, which really, if you have a big corpus, you can easily predict the word that comes next, and you always know the word that comes next as your ground truth, right? And they did that and then followed it up with uh, a fine tuning stage, and they got interesting results. Then decided to scale it up in GPT-2 to, I think, about 1.3 billion parameters model, and then saw interesting result, which was the idea of the paper was called Language Models Are Multi-Task Learners, right? Which they saw interesting results like, okay, the model is able to actually do tasks that it wasn't explicitly trained for. Then the GPT-3 paper with the 173 billion parameter model came out, and it became clear that when you scale up number of parameters, you end up with this few shot learning capability, which is you could state a task, give the model a couple of examples on how the task should be executed, and then have the model execute the task, right?
Yeah.
And then that led us to this idea of few shot learning, or in context learning, rather, which means you don't have to do gradient updates. Since the model has gone through a large pre-training stage, it has somehow absorbed knowledge, and then it uses that knowledge in context, which means you could give it a task and set of examples, and you could ask it to solve a problem, and it's able to do that without gradient updates.
Mm-hmm.
And the interesting thing about the GPT-3 paper was that GPT-3 was a giant auto completion model, right? So it's not good at following instruction because it wasn't trained to follow instruction, right? So the few shot learning is how you get it to actually perform tasks, and you expect it that, okay, if I give it instruction or translate this to this and I give it examples, then I expect it to kind of like just follow up on that and complete the tasks, right?
Mm-hmm.
And I think that was kind of known from GPT-2, not just GPT-3. But then you have the Instruct GPT paper, which OpenAI followed up with, and it's this idea of, I think, the idea of um, training the model to learn to follow instruction, right? I'm not sure which paper came first, but there was a paper from Google also that has to do with what kind of like introduce what we now call instruction fine tuning today,
Yeah. Mm-hmm.
right? So those two papers kind of like showed that if you have a couple of high quality examples and you train the model in a supervised learning way on those high quality examples, the model learns to follow instructions better.
Yeah.
Of course, the
J-
Instruct GPT paper took it a step further by introducing what we now call RLHF,
yeah.
right? Which is reinforcement learning through human feedback.
Mm-hmm.
So essentially, we arrive at this point where models were first giant autocomplete machines to being able to follow instructions. So you could tell it to summarize a text, and it can do that. You could tell it to tell a story or explain a concept to you like you are 5 years old, and it could do that. So we had this instruction following capability. And then two papers that I think really made it clear was the scaling law paper from OpenAI by Kaplan at first, which kind of like showed that if you keep increasing the parameters of the model, the loss keep going down. essentially. And then the chinchilla scaling law paper, we showed that you have this relationship between the loss, the number of parameters, and also the number of tokens you have in your data set. And I
Yeah.
think the chinchilla scaling laws from Google was the one that kind of like showed that GPT-3 was undertrained because it has a lot of parameters, but it was trained on less tokens. And they showed by training, I think, yeah, a smaller model about I'm not sure the number of parameter, but I think about 70 billion parameter model, which was way less than what GPT-3 had. And then they show that by increasing the number of tokens you train on, your loss keeps going down. And that's kind of like showed that okay, if we can train on more tokens, essentially you can hold your number of parameters constant, but increase the number of tokens you train on, you can easily have a really, really good model. Right?
Yeah.
And that's ushered in this age of scaling, right? That okay, we now we sort of like entered into this era where a 7 billion parameter model that is trained on a lot of tokens could actually be extremely good at instruction following and everything you need it to do. So you don't always need a big model, right? But at the same time, if you have the capacity to increase the number of models and at the same time drastically increase the number of tokens you train on, that is even better, right? So I think um, GPT-3 was trained on, and I might be wrong, but I think around 600 billion tokens. But now we have smaller models that are trained on like 7 trillion tokens right now, 3 trillion tokens, 4 trillion tokens, which is almost 10x of what GPT-3 was actually trained on, which shows that those models are now much more capable than GPT-3. So you have that pre-training stage, then you follow it up with supervised fine-tuning, SFT. Um, I might be wrong, but I think the Llama 1 and 2 papers were the one that kind of like made SFT a buzzword, right? Which means if high quality tokens, you train on them, you have good instruction following capabilities to use, and so on and so forth, right? And then you follow it up with RLHF as a and some other sort of polishing stage to have the model um, really be a good chat model, which is what we have today in ChatGPT. So yeah, those are kind of like the interesting developments. And right now, everybody is concerned that we are getting to the end of that scaling. So
Yeah.
the idea was that I mean, if you are going to keep scaling, that means the hardware companies make a lot of money, right? Because
Yeah. Yeah.
they sell they sell more GPUs, which you then
Yeah.
need to like um do your computation on.
Yeah.
And which is pretty interesting because I think this is where I love Grok with a Q, the language processing unit company, because they focused on an interesting part of the problem, which is inference, like you mentioned. And the truth is, you train once, although it takes a while to train these models and it can be difficult, unstable, and so on. But once you get the recipe for training, you train, then you deploy, and then people begin to interact. And I think in the long run, far much more money and resources will be spent on inference than training, right? Because a model can sort of, permit me for the lack of word, um, live forever in that inference mode,
Yeah, yeah, yeah.
right? So which means people will continue to interact with it, the model will continue to produce more tokens and so on and so forth. So inference becomes really, really important, right? Which then kind of like led to series of innovations that happened last year on test time compute, right? Which is this idea of problems with varying complexity should use varying resources, right? Because initially what we were doing was that you have a prompt, you give it, the model just spill out results, right?
Yeah,
So
yeah.
regardless of the complexity of the prompt you give the model would always just spill out the results without thinking. And then we had this idea of um, two two ideas actually, which is process supervision and output or outcome supervision, right? Which is, can you guide each of the steps of the model as it tries to solve a problem, or do you just supervise the output of the model? But essentially, what you're trying to do is to introduce this idea of some sort of search through the output of the model. So rather than the model doing just spilling out all the output tokens at once, I would say essentially what you're trying to do is you're trying to get the model to carefully choose what tokens it should output depending on how complex the problem is,
Mm.
right? So you have things like best of n, where the model, instead of generating one single output, generates n outputs on a particular problem. And then you have some sort of voting mechanism or whatever, a reward model that chooses the best output, right? You could somehow combine all the n generations to form a single generation and to give best of all the n words, right?
Yeah.
So uh, that's kind of like the idea of test time compute, because people saw that we need to spend more time on inference, and it makes absolutely no sense to say you give a model a simple question like 2 plus 2, the way you give it to a human, you don't want it to spend to just, I mean, 2 plus 2, you would expect the answer to be fast compared to when you ask it to do, say, some complex
Like a
algebraic.
differential equation. Yeah.
Exactly right. So 2 plus 2 to a person is just 4, right? But when you say, okay, find the differential of, say, some sort of trigonometric function, then the person has to put pen to paper and try to solve that out, right? So you want that kind of capability in the model where simple questions you always just use less resources than really difficult problem, which then leads to what we are now experiencing with reasoning, right? Where
Yeah.
models think before they um, they give an answer, and you expect that the more complex the problem, the more the thinking budget the model has to use. So you have this concept of thinking budget, which is the number of tokens the model essentially spends on thinking before it outputs an answer, which means it should use a smaller budget for really easy questions and use a larger budget for really difficult problems,
Yeah.
right? So
Yeah.
now we are now settling into the fact that, yeah, training is really important, but inference is where humans begin to interact with these things. So
Yeah.
over the last couple of months, I think everybody has been really, really serious about inference. Yeah.
Yeah. I think maybe a lot of the investment on inference now is just because, people are using it more and more. And so it's like we can't really scale back anymore. We just have to
Mm,
keep scaling up. And so inference just becomes like a big thing now. You
yeah.
need to keep, because every single day, maybe new people are signing up for this kind of things and new tasks that people might have. And so you just need to have models available in real time
Mm,
for this kind of things. But I want to touch on something you talk about in like your verifying history. This idea of just purely supervised versus reinforcement learning for human feedback, just RLHF, I think. And
yeah.
then because you said, I know some people might not be aware about what token means, and then maybe just give a small history, NLP, natural language processing history of how we take data, text, for example, how we take
Mm,
text and turn them into tokens and stuff like that. And I know a lot of people are aware of people who use these platforms, like especially chat, know about reasoning and thinking, so they can actually maybe already know what that test time compute looks like. Which is the
mm.
thing you talked about. Yeah.
Oh, okay. So first of all, I'm not an expert on tokenization, but I will try my best to explain. So usually you have what you call a corpus, which is a body of text, right? It could refer to a corpus could be all the text on the internet, or it could be all the texts in a corpus could be all their reporter books, right? Or all of um um Tolkien's books, right? That could represent a corpus. That's a corpus. And what you want to do is you want to essentially create tokens from the corpus, the body of text. You are trying to model the joint probability distribution over tokens, right? So which means you want the model to learn to predict what should come next after a particular token. Now, tokens could be words. I mean, the easiest way to think about tokens is as words. A body of text is composed of words, right? Let's take English language, for example. You have words that if you read through a text is made up of words, essentially. And you have punctuation marks and so on and so forth. So those are words, those are tokens. In the simplest way to think about it, you can think of words as tokens. Usually, you take your corpus and it goes through this process of tokenization, which is where you create what you call a vocabulary, right? So a vocabulary of a corpus just refers to all the unique tokens, or if we are taking tokens as words, all the unique words in that particular body of text that forms your vocabulary, right? In modern day LLMs and so on, your tokenization process is usually done by a byte pair um, tokenization process, which is instead of having words, you break up the words into chunks, right? I won't go into the details of the byte pair encoding tokenization process, but essentially you can just think of token as words. So once you have a vocabulary of words, which is all the unique words in your corpus, what you want to do is that you want the model to learn how to create coherent sentences from the vocabulary of words you have. And the way you do that is that you train the model on that corpus, right? And you hope that at the end of the training, the model knows how to write. So say, for example, you train the model on all the Harry Potter books. You would expect that at the end of the training, the model knows how to write like J.K. Rowling, right? At least your model should be able to memorize all of the Harry Potter books, even if it's not creative, and I use creative in quotes, even if it's not creative
Mm-hmm.
to give you interesting result, it should at least have memorized the entire text and know how those tokens should follow. Right. So essentially, tokens are just words, which you then use to build a vocabulary, which the model then learns joint distribution of words or how to form words from that vocabulary.
Mm.
So I don't know if that makes sense.
That makes sense. Yeah. I didn't want you to go too much into the details to lose people, but yeah. Um, yeah. So I think this, like, just going back again to that idea of supervised learning
Mm.
and reinforcement learning for human theory, because that was a really genuine idea at the time, original idea, the RLFH that
Yeah.
produces the chat models that we have now. Yeah.
Yes. So with RLHF, you have this idea of because RLHF is reinforcement learning through human feedback, you have this definition of terms coming into the picture because you're taking the idea from reinforcement learning. So you have this idea of calling an LLM a policy, right? Which is some way to make decision, in our own case, generate outputs. And usually you want to start off with what you call a supervised policy, which is basically a pre-trained LLM that has passed through supervised fine-tuning, SFT. And what you are doing in supervised fine-tuning is that, like I said, your pre-trained model or the result of training is just a giant LLM that is an auto-completing machine. So it only spews out tokens mindlessly. I mean, everything spews out tokens mindlessly, but the point is, it's that it's been trained on
Yeah.
on on next token prediction. So it doesn't follow instruction. It's just kind of like spilling out what it feels is the next token. So what you want to do is that you want to take it through supervised fine tuning, where you structure your data as prompt completion, prompt completion, prompt completion. So you collect a large data set where you have prompt completion pairs. And then given the prompt, so this becomes kind of like a conditional probability thing, which is given the prompt to the model, you want the model to generate some sort of completion. Then you match the completion of the model with the ground truth, and then you back propagate, right? So it's just like the regular supervised learning we know, which is giving some X, you want the model to predict a Y, and then you have a loss function that checks the Y of the model against the ground truth, then you back propagate the error. And that is basically what you are doing in supervised fine tuning. So the model learns how to complete prompts better, right? So given some sort of context or some sort of prompts, the output becomes much more polished compared to pre-training or what you get from pre-training. And you can also train the model to learn to use tools this way also, right? So prompt completion, where the completion can be some sort of tool use, right? And so on and so forth. But I won't get into that.
Yeah.
So once you have a supervised policy, which is the model that has now passed through SFT, then you want to do RLHF on that model. And basically, what you're trying to achieve with RLHF is that from the name, reinforcement learning through human feedback. What you're trying to do is you're trying to align the model to sound more or to imbibe human stylistics or human style of writing. So you are kind of like training the model to be better at generating outputs that sounds much more human-like. So essentially, you train the model to generate outputs, and then you judge those outputs based on human feedback. So you assign scores to those outputs, and then you back propagate. So you would have a reward model which has been trained in such a way that it can tell, giving two inputs or whatever, two outputs. Maybe you give a prompt to the model, the model generates completion A, completion B, completion C, completion D. You want the reward model to kind of assign score to each of those completions, right? So, which means you also have to train the reward model.
Yeah.
And usually, your reward model would start from the SFT checkpoint of the LLM, which is the supervised policy, right? And that is essentially what you're trying to do with RLHF. So you are trying
Yeah.
to have the model align with human style, right? So
Yeah.
which means you can decide to um the way people write things, or but there is a little problem with that because you cannot always you can't collect data from all the humans existing, so you still end up having a really small sample
Yeah. Yeah.
to train the model, right? But because the model has gone through this stage of pre-training over the internet, you expect that that stage of polishing should be enough to kind of like bring out those latent styles from the model, right? Like my manager would say, that big models are always sample efficient, which means you don't need a lot of training samples to get them to do what you want them to do, except if such skill or what you are trying to get it to do was not in the pre-training data in the first place.
Mm.
But if what you're trying to get the model to do is very in distribution, which means the model has probably seen it during pre-training, then it's easy to do things like RLHF and SFT to actually bring out that sort of style. So
Yeah.
yeah, essentially it's kind of like stylistics at that point. Yeah.
Yeah. Yeah, I know we're talking about because this whole idea of RLFH is a very good idea and like how to sort of like I guess align a model with certain type of tasks that you might want. But like I wanted to go back to reinforcement learning itself, like pure reinforcement learning and how some of these ideas, come about like state, action, reward, policy. What a policy is how to act, reward is
Mm,
if I do something and the reward I get outside of doing something, I could get a bad reward for doing something that's not good, get a good
mm,
reward for doing something that's good. And then a state
mm,
and an action, like the action would probably be the maybe text I output. But this whole idea of reinforcement learning, it has actually come back now a lot, but like reinforcement learning through human feedback sort of borrowed some of this terminologies and ideas that like and methods that pure reinforcement
Yeah.
learning has developed through the years.
Mm. Yeah. I mean, so what we have right now, which became popular through the work of AI2, which is Allen Institute of Artificial Intelligence. So they released a paper, I think, last year called Tulu 3. Was it Tulu 3? Yeah, I think it was Tulu 3. I'm not sure, but yeah, I think it was released towards the end of last year where they introduced the concept of reinforcement learning with verifiable rewards, right? Which what they basically did was, like you said, they borrowed this concept of policy, taking action, observation, and so on and so forth. So in the case of the LLM, the starting policy is the supervised fine-tuned model. You give it some sort of state, which we could represent as the entire context um, given at the very beginning, and then it proceeds to take an action, which is generates the next token based on the initial state you've given it. So it generates the next token. Then now you have a new state, which is the previous state plus the new token that has been generated. And then it takes another action, which is generate a new token based on the new state, and then it adds that. I think it's kind of like an ad hoc reinforcement learning, right? But
Yeah.
then it works because you have the problem of um, do you assign you want to optimize for good for reward, right? So you want the model to kind of accumulate reward over time. But then there is the question of, do you want to score individual tokens that are being generated, which is where uh, the concept of a value function comes in, right? Which means every action you take, you want to kind of like score what you get from that, or do you want to score at the end, right? And for reinforcement learning with verifiable rewards, what we basically do is that we assign a reward at the end.
Mm.
And that is easy for things like um, mathematics and code, where output is expected to be some value or some sort of precise computation. So for mathematics, you expect a final answer and you can check the final answer, right? So it's easy to do reinforcement learning with verifiable reward because you could easily say, I'm giving you this question, I need you to solve it, then the model solves it, and you are only concerned about the final answer, and you check that, oh, the model gets to the final answer, here is a reward, right? And I think that's kind of like similar to what you are doing with RLHF also,
Yeah.
right?
Yeah, exactly.
Because with RLHF, you have multiple outputs from the model, and then you also score, right, using a reward model.
Yeah.
But now the real distinct thing about RLVR, reinforcement learning with verifiable rewards, is that you can completely ditch the reward model,
Hmm.
right? Because you don't need an extra model to score mathematics answer. Because given a question, you could just get a bunch of mathematics questions and answers from the internet,
Yeah.
and you have some sort of regex um, pattern matching algorithm that just picks the final answer of the model and matches it against So you have a strict matching algorithm that just matches it against the ground truth and see if the model is right or wrong.
Yeah.
So you don't need to deploy an extra reward model
Yeah. Okay.
to do that,
Yeah.
right?
I was thinking
So yeah.
because like mathematics usually follows a process, or the way like maybe physics, for example, usually follows a process to get to the
Mm.
answer. Are we also checking that pathway towards getting to that answer?
So like I discussed on the when I mentioned test time compute that you could do process supervision or you could do output or outcome supervision. In process supervision, you are very concerned about each of the steps. So usually you would score the student steps, at least in Nigeria, you will score the student steps before you score the final answer.
Yeah.
But in this case, you are not scoring the steps, you are scoring just the final answer, which kind of like introduces all sort of problems, right? For example, with DeepSeek R1, which followed up on the Tulu 3 method of reinforcement learning with verifiable reward, the DeepSeek R1 is a verbose model because it does all these, it outputs all these tokens, reasoning tokens or thinking tokens, as we would call them, and gets an answer, but they are usually long. And that's because there is no training signal for the reasoning process. You are only getting a signal at the end
Hmm.
of the thinking process, which means when you get an answer.
Yeah.
So it's as though we have the question, we almost don't concern ourselves with what is happening in between the question and the answer. We're only concerned about the answer. And that
Yeah.
is why when you look through some of those traces, you could see the model backtrack a lot or second guessing itself, even when it has actually gotten the answer at the very beginning. So you have this problem of overthinking, right?
Yeah.
And you also have the problem of underthinking too. And that's because there is really no process signal. And really, when you think about it, it is hard to kind of like have a process reward model that would have to score every single step. Because first of all, you have to define what a step is, right? So, what is a step? If we call them thinking tokens, then the question is, what is a thought? Are you scoring thoughts? Are you trying to get the model to backtrack better or remove backtracking altogether? You have all these sort of questions you have to answer. I worked on that problem during my internship at Cohere, right? And there's also a paper on, I think it was from the guys from NVIDIA, Retro Search, where they try to break up the reasoning chain or the reasoning trace into what you call thoughts, right? Self contained paragraphs, and see if you can actually make it much more efficient. But essentially, you only get the signal at the end, which then lead to all sort of interesting behaviors. Yeah.
Yeah. Yeah. That's really good. I think one of the things that I'm seeing, throughout this conversation is just so the history of ideas, and like how certain ideas lead to other ideas, and then how we take that up and then that generates a new idea. Because just going from the very foundations of NLP, for example, when we used to do naive based classifiers, to generate to know if something is a spam or not, in an email is a spam or not.
Mm,
Sentiment analysis, for example, those kind of very simple NLP analysis, natural language processing, for those who might not be familiar, like those kind of analysis to what we're doing now. And it's just like ideas, 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 ideas. And I was listening to Ilya the other day, and which is sort of like a sentiment that I've sort of like noticed in throughout almost this year, is this sentiment that we're running out of ideas, and like there are sort of like
Mm.
no new ideas, and some of the things that we're doing is just scaling models and not necessarily generating new frameworks or ideas to sort of like push the boundaries. And I don't know if you feel that too, because you're also doing a lot of active research in this space. I'm doing research, but like not necessarily in NLM. So I'm doing ML research for like science. I wonder if this whole thing of lack of ideas is true, because I think in 2025 we our ability to execute is even more than the sort of good idea, more than the good ideas that we have right now. So
Hmm. Yeah.
I wonder if this whole concern of lack of ideas is really sort of like going into this research cycle, because we actually need good ideas. We can't keep doing what we're doing. We can't keep scaling up. It's not sustainable, ever, like hardware wise, financial, the secular deals that are happening, environment, and all that and all that. So I wonder if you've been thinking about that, or you have like cool thoughts on this whole problem of lack of ideas.
Yeah. So I think for this year, we've seen a lot of interesting ideas in agents, agent orchestration with a long horizon problem where the agent deep research, where the agents do a couple of things for like 10 minutes. You have the idea of sub-agents for coding, especially in coding. I think these are really, really interesting ideas. Then you have attempts at memory, episodic memory, procedural memory, semantic memory, and so on. Um, Model being able to like learn from experience and things like that. I think these are active areas that people are looking into. I've forgotten who said this. Probably it was Max Planck that, in relation to physics, he said this the study of physics is the study of the history of physics. And I think that also applies to AI. One thing I love to do is to kind of trace ideas back to the beginning, because sometimes there are usually ideas that are lost in time, which might be very essential to what we are doing today, right? And there are people who have said that, oh, we also need a new architecture or a new kind of way of doing deep learning. And of course, there have been new kind of like new architecture, like state space machines with yeah, the Mamba paper, and there are companies that are using state space models, rather SSMs, that are actively using them. But I think next year, with some kind of work coming from the guys at Google with nested learning and Titan, which are interesting ideas also. Like Ilya said on Dewakesh's podcast, that it's time to go back to the age of research, right? I think now that it looks like we are, of course, there are still a lot of interest, and this is it. There are still a lot of interesting things we can still do with current systems. There are really, really interesting stuff we can still do with current systems. But we are kind of like eating some sort of war, and I think that would prompt a lot of us to begin to look deeply into some really interesting stuff. I think probably, and kind of like the way I've forgotten his name now. I think his name is pronounced Sean Yao. I don't want to mess up his name, but he was the author of the React paper. the reasoning and acting paper, he wrote a blog post called AI Halftime, and he
Mhm.
mentioned that we are in what is called the AI halftime, right? So, which means there is going to be a new breakthrough around the corner, and we know for sure, right? And ideas around continual learning, memory, long-term learning, and so on and so forth are things that people are really, really thinking about. But at the same time, there is also the short-term gain of the current systems, which are really, really good, right? So yeah, I think it's kind of like balancing short-term gains and also long-term rewards, right? You could either focus on short-term gains and see if you can squeeze more performance out of the current systems, or you could take a step back and look 10 years into the future and try to like think of solve the hard problems, right? So depending on where you are, I think there are going to be people that would continue to maximize or max out the short-term gains because the systems right now are really good. And there are people that would look into better ideas for the future. But I
Yeah.
think whatever we have today would still be a big part of whatever those new ideas would be. Yeah.
Yeah, so it's this classic exploits dilemma.
Exactly.
Should we keep
Exactly.
doing what we're doing, or should we find better ways to do what we're doing? Yeah, because like there's already so much invested into what we're doing right now. So people want to see the benefits of that as opposed to seeing if we can keep doing research just to see if we can. Um, so I guess even if anybody's doing inference right now, they might be solely focused on that, if except they're just a pure research company like what I guess Ilya is
Mm,
doing or whatever the former CTO of OpenAI is doing right now. I don't know if they're doing research, but
mm, mm.
but
Yeah.
yes,
That is thinking machines, right?
yes,
Yeah.
yeah. So
Yeah.
I want to go to this whole idea of like the tooling and like the terminologies of like, right now what we're doing, we start with just like text. And
Mm,
then we saw people talking about tools, you know, this whole idea of using tools. And then we started with prompting, I think prompting before tools, prompt engineering, a lot of prompt engineering, then
mm,
tools, then React, like the React framework you talked about. So you make an action, observe, and then make actions based on that observation, and then keep doing that in a loop until you have the results that you desire. And then from tools, we went to
MCPs.
yeah, MCPs, and then we sort of like wanted to create a standard layer for tool interaction. And then right now, a lot of people are talking about context engineering, although I don't really know how that's very different from prompt engineering, because it's prompts are still context in a way. Anything you give to your agent is context, and maybe
Mm,
context engineering. So I'm guessing it borrows a lot from the RAG, the retriever augmented
mm,
generation, where maybe you're engineering how you're retrieving and passing it to the LLM. I guess that's what I've not really looked into it. Maybe you can speak on it, but like, for people who are
yeah.
doing RAGs, and I wonder how the architecture has changed now. I know people are still using RAGs, but like, I wonder if context engineering or tool usage sort of like
Mm, mm,
changes some of that architecture.
yeah. So, um, like I said, I think all these things belong to short-term ideas that are trying to maximize the current architectures we have, right? And they are really, really working, right? So with things like MCPs and tool use, of course, can train a model to learn how to use tools by uh, simply outputting some sort of JSON format with what parameters to be passed into the tool, and you make a tool call and you get a response. Your response can either be a valid response or it can be some sort of error to tell the model that, okay, did not give me the right parameter, then the model retries and so on and so forth. So to bring in MCP, you kind of have a sandbox where you can install all the dependencies of the tools and everything, because a tool is essentially some sort of code, right? So you can sandbox that away and have it outside the LLM itself, and then you make a call to it, some sort of call to it, and it gets some sort of response. So it's really nice, and you can put all your interesting stuffs on an MCP server, and you just have the model call them, make a call to the MCP server, and get some sort of result. And with context engineering and things like skills, which Anthropic introduced, with context engineering, you are asking the question, what sort of information should I put in the context window of the model to kind of like get the model to behave properly or to maximize the performance of the model, right? And really, when you think about it, humans are kind of like good in what I would call selective attention, which means with all the conversation we've been having, somehow our brain is able to compress bits and part of this conversation. And, people create what they call bullet points,
Yeah.
right? Which are
Yeah.
like the key points in a conversation and so on and so forth. So you want the model to like pay rapt attention or to know what should help it to perform better, right? And that's essentially is what you're trying to do with context engineering, right? So you're trying to find the best context, shall I call it configuration, that can give the desirable result or behavior you want. With prompt engineering, you fit these instructions, and as the model generates output, you add the output of the model to the history, and then you put that in the context of the model, and then you have a user message again. The model generates an output. You keep on adding that into the context of the model. The problem with that is that if you have a long horizon task, you end up blowing up the context of the model.
Mm.
And then you have this concept of, I'm trying to find the word Anthropic used in the article. They use the word, I think, context rot,
Yeah.
right? So, and this comes from, I remember in 2024 when I was a research scholar at Cohere, I looked into this Lost in the Middle paper, where it's kind of like a precursor to the needle in the haystack type of benchmark, where you hide something at the beginning of the model and you tell the model to retrieve it, you hide it at the middle, and you tell the model to retrieve it, you hide it at the end, and you tell the model to retrieve it. The problem is that when you put it at the beginning or at the end or very close to the end, the model is able to actually retrieve it. But when you hide it at the middle, within the context, it becomes really difficult for the model to actually recall the information accurately, right? So you have that problem, which means even though context length has greatly increased, we are coming from like 512 context length, 4K, 2K context length to now a million, 10 million context length.
Yeah.
But you still also want to manage the information you put in that context so that they are well curated, and you don't want a case of context rot,
Mm.
right? So it's a question of what should I put in? And it's kind of leads, because you could think of the context as some sort of short-term memory, because the model is kind of like stateless. LLMs are stateless, right? They only
Yeah.
remember what is within their context. The
Yeah.
moment you evict information from their context, they don't really remember,
Yeah.
right? So, which means how you manage the tokens in the context really, really matter, right? So now that we have cases where we give docs we give documents to the model, we give images to the model, the model make a tool call, you have the tool call in the context, you want the model to retrieve some sort of past history and so on and so forth, right? So which means you want to carefully put those relevant information, make them compact, and this could come through, say, some sort of summarization or note taking and so on and so forth, or some sort of memory tool that the model can call and say, okay, I'm making a call to this memory to get me some information from some trajectory that I've actually done.
Yeah. Yeah.
And
Yeah.
you have that information put in the context,
Mm. Yeah.
right? So that's exactly what you're trying to do
Yeah.
with context
Yeah.
engineering.
Yeah. It's
I've,
really
I've,
interesting.
yeah, yeah, yeah. Go ahead.
It's really interesting because when I think about the challenges of context rot, for example, the challenge of context rot, for example, and I wanted you to finish, but like if I think about like a more continual system where we sort of like learn gradually, we probably might not have this problem. I know we've talked about, you mentioned continual AI, but like we probably would just maybe talk about it for like 5 minutes and how like continual AI might be able to sort of like fix this problem of like context.
Hmm. So when you say continual AI, you would mean continual learning, right?
Yes, yeah.
So kind of like the way I think of continual learning is you, so let's say the context is the short-term memory, right? So whatever is in the context, the model remembers. But there is also the long-term memory, which is the weights, right? This is kind of like the information that comes through training, which the model, I would use the word forever remembers, right? And with continual learning, you want a case where a model performs a task, it succeeds at that task, then it sees a similar task sometime in the future, and it's able to recollect that it has done some sort of task like that, and it might be helpful to refer to that, which then makes it more efficient in doing the new task, right? So you have this concept of recall from history, and you have this concept of applying whatever you recall to the current problem. So there has to be this relevance between what you recall and what problem we are trying to solve. So then you have the question of recall from where, right? Should it recall from somewhere outside its weight, which means you have all the past history or past conversations or whatever it is stored somewhere and it records from there? Or should you offload memory or past history intermittently into the weights so that they become a part of the internal knowledge of the model? And this is something I think about because with humans, we do something over and over again, or we are in similar humans kind of like there are cases where we do zero shots
Yeah, yeah.
because with zero shot stacks, because we've seen a similar tax and we kind of like just bring that. Then there are cases where we single shot tax, which means we see an example and then we apply the tips of that example to the new tax,
Mm-hmm.
right? But the reason why humans are capable of zero shorting tax is because they remember the important bits of a relevant tax, which means they recall from some sort of long-term memory mechanism. Of course, I'm not a neuroscience expert, so I really don't know the exact mechanism for that.
Yeah, yeah, yeah.
So, which means we need to do the same for the models themselves. And we need to be able to test how well the model is able to recall from its own internal knowledge. Of course, when you give a question to the model, if you don't have the model use any tool or connect to the internet or make an API search call or whatever, it tries to solve the problem using its own internal knowledge without making any tool call. So it thinks through the problem and it tries to solve it. But then there is the question of how reliable is the internal knowledge of the model, because we've seen we've seen models falter on really simple math problems, right? But essentially, you have in continual learning, of course, I don't have the answer, but you want this recall from history, this concept of relevance between what is recorded and what task you are trying to solve, and this concept of distilling whatever is recalled and applying it to that particular problem,
Mm.
right? So that is how I'm thinking about continual learning. The specifics now is how do you do that, right? Do you intermittently, or there is the concept of, I think this was something I looked at this year. Then Kapati talked about it, which is system prompt learning, which is this idea of giving the model the ability to make edits to its system prompt if it comes across new knowledge, right? So
Mm. Mm.
it should be able to like kind of like annotate new things in its system prompt. But then there's the question of, okay, what happens when the system prompt becomes extremely large? Then we have the problem of context routes
Yeah,
again.
yeah.
Then context engineering becomes important. Or should we offload whatever has been learned over time into some sort of long-term memory, which is we retrain the model? The question is, how do we efficiently do that? Right. So these are some of like the questions we need to solve.
Yeah.
But I think, yeah, it's kind of like a good direction to be taken.
Yeah. And I think, in the past years or so, I've been seeing a lot of startups doing stuff on memory, just memory alone, like,
Mm,
yeah, I've seen a couple startups just focusing on memory. And I wonder how much more relevant that would be in the next coming years. But like, I usually only thought of memory as more of like a vector database, but apparently not because um
yeah.
the way
So I,
they
I
engineer it is
think,
different.
yeah, I think most people see memory as some sort of tool call, right? So you make some sort of tool call to something that gives you bunch of text, which you can then put in the context, right? I'm not really familiar with almost, but I know that the memory tool is what most people use right now.
Yeah.
So they have some sort of memory tool, right?
Yeah. Yeah.
Crash pad memory or whatever
Yeah.
it is.
Yeah. Yeah.
Give it a edit access, write access,
Yeah.
read access, and so on. Yeah.
Yeah. So I think, we've spent a lot of time. So just to sort of like start rounding up, I wanted to talk about um I think two questions in one would be your own trajectory doing mechanical engineering now and doing AI work, and I guess what sort of ideas or I guess skills should like an ambitious kid in a university or college be working on right now? What kind of skills should they be developing for them to be able to contribute to the frontiers of like intelligence research? Because like we're going into the age of intelligence, and intelligence is going to be cheap. We've been hearing that phrase, intelligence that's too cheap to meter. So like the
Mm,
average person augmenting themselves with tools would be even much more smart. So I wonder what kind
mm,
of tools, and I think that, uh, just generally, I think that everything is becoming more competitive.
yeah.
Because by and large, the tools are sort of democratized in a way. So like everybody's becoming competitive. Of course, although of course, if you have access to the internet and stuff like that. So I wonder
Mm,
what kind of tools, what kind of skills, what kind of knowledge should people be gaining if they want to sort of like be very competitive or contribute at the highest level, looking at your own background.
mm. So I think the entry point to AI is constantly evolving because when I started studying in 2017, um, generative AI was just kind of like coming into place. And even when I started studying, I did not know anything about generative AI. Right? We start with the classical ML, you learn about linear regression models, you learn about all this, um, a little bit of representation learning, and so on and so forth. So you have this math heavy background you start with, then you learn to write things in Python before you then move to neural networks, right? And nowadays, neural networks is at the very center of everything. And I remember when I was learning about the GPT paper, one way that I learned was to write the self-attention blocks from scratch just to understand how exactly they work. And also, when I was learning back propagation, I would draw a two-layer neural network with just two neurons on paper and try to like solve by hand how back propagation would work. So I think in those two instances, what stands out is learning from experience, right? So rather than try to like go through a book end to end, you pick an entry point and then you learn by doing projects. Of course, you should know how to code, right? That should be the first thing. So which means Python is widely used in the ML community. You should know how to write code in Python and then just build. In the process of building, things are going to be really hard at the beginning, but slowly you would learn what you need to learn. You would know where the deficiencies are. Of course, you could read through. So there's this nice beginner book that by I think his name is Michael Nielsen, neural network and deep learning.com, or go through 3Blue 1 Brown videos on neural networks. That kind of like give you a starting point of what neural networks are. Then the rest is up to you as to how you want to build those things. So I think learning by building stuff, which is kind of like depth first learning, you have some sort of project you're interested in and you kind of build it brick by brick, might actually be a better way to get into the field compared to how I got into the field, which is start with the linear algebra, start with the mathematics, know what linear regression is, then slowly move into neural networks and so on and so forth. And yeah, that might be a longer route than what most people need right now. So, and the good thing is there are a lot of communities and unconventional entry points. I got my first big break thanks to Cohere Labs, which is the non-profit the research lab of Cohere. They have this open science community and they have a research scholars program, which is for promising researchers, early researchers from unconventional backgrounds, which was really, really helpful, right? So they don't care if you don't have a PhD or not. And that really was helpful for me, right? So I'm giving a massive shout out to Cohere Labs and Cohere for that. So I think those kind of unconventional background, especially for people from Africa like me, that have limited opportunities, I think those are kind of like entry points to actually explore. Belonging to the community, seeing what people are doing, try to contribute to what people are doing, are kind of like the best way to learn.
Yeah.
Yeah.
Yeah, I think, yeah, to be honest, your point on, actually coming from Nigeria and just like doing research at that level is really important because even for me doing a PhD, I think that the quality of people I am surrounded with sort of like changes how you think about problems, how you think about approaching problems. And like, this is something of course, when I was in OAU, there was a lot of hunger and like
Mm,
passion and actually passion, talent, hunger, skill, but a lot of resources were lacking. And I think that's just where, the difference is, about really what, if you're going to do research at like the top level, just like resources are sometimes lacking, which is sort of like the missing thing there because there's already like hunger and skill and talent and all that stuff, but like just more resources and stuff. Yeah.
yeah,
And
yeah.
it's really interesting when, a couple of people can sort of like get close to resources and what they can do. Yeah.
Mm, mm, mm. Agree, agree.
Yeah. So we're sort of like closing now, but like there's a question I ask every single person who comes on this podcast. And I haven't asked this question in a while because I haven't done a podcast in a few months. But the question is, what's the meaning of life?
Mm. Interesting. I mean, I think your worldview kind of influences how you define life in general. And for me, I have a Christian worldview, which kind of like defines what life is, right? And from the Christian worldview, we know whatever we do here is temporal, and in the end, we would answer for whatever we've done here, and that the road to salvation is through Jesus Christ. But from a living the Christian worldview, I think from a philosophical and scientific standpoint, like to quote Einstein, who said curiosity has its own reason for existence, right? I believe being curious about the world around me gives me this um meaning because, and you probably know this, I really don't give talks. This is my first podcast ever, so I don't do a lot of public speaking because for me, I'm just curious about finding out stuff. And I think that has come to define most of what I do. And then I believe that our tastes evolves as we grow. So which means probably I will get to a stage where I'm in a position to give or pour myself out to people. Right? So right now I'm still a bit selfish with my time and
Yeah.
stuff. So in essence, I would say to love God, to be curious about the world, to be curious about the natural things, to really want to pursue knowledge for its own sake, to be curious for its own sake, not because of any material gain, but just to want to find out stuff by itself. Because that in itself, I think, is beautiful and exciting. I think that is what has those two things have kind of like defined life for me,
Hmm. Hmm.
right? So I'm curious about God. I'm also curious about creation in general, right? Which has led me through mathematics to physics to AI and maybe some other thing in the future, right? But it's more like this itch to try to understand things. As of course, there are some things that are beyond comprehension, but just an attempt to understand satisfies me.
Yeah.
And I would say that that kind of like defines life for me.
Yeah. Thanks for the beautiful answer. It's really good. Yeah. Curiosity, knowing, and faith,
Yeah.
and actually introspection before giving out and stuff. Yeah. Really, really good. Yeah. Thanks for coming on the podcast. It was really good having you here. I think I learned so much myself, and I know that like the interneuron community are also gonna learn so much from this conversation. It was really nice to hear about like what has been done and like where we're going in the next.
Yeah. Thanks for having me too.
Thank you for listening to the end. If you enjoyed the episode, I'm glad that you did. Don't forget to like, share, subscribe, all that stuff. Like I said in the introduction, I plan on doing 6 quality episodes this year. So if you like this long form conversations, you can also reach out to me to tell me what you would like to listen to on the podcast, and I could make that happen for you. So yeah, that's it for me this week. See you next time, and until then, stay curious.